Good morning. Today we are going to learn about reaction theory, partial wave analysis of nuclear reactions, and using that we are going to estimate the cross section for reaction as well as scattering process. I am Dr. Raghu A, working at Government College Autonomous Mandya. So this is the outline of the talk. First, let us begin with scattering process. So here what you are seeing is a set of parallel lines which represents a plane wave traveling from left to right. Psi in is actually incident wave function having a single value of momentum k. So k is a represent of monochromatic wave. Now the separation between these parallel lines represents the wavelength of the plane wave traveling from left to right. Right side a target is kept. When the incident wave incidents on the target, it gets scattered in all possible direction, spherically symmetric and extending radially outwards in this manner. So incident wave is assumed to be traveling from left to right with momentum k, and scattered wave will get scattered with a spherical symmetry in all possible direction with a momentum k prime. So if detector is kept at an angle theta, then the scattered wave can be measured using a detector. This is actually a process, scattering process that normally happens. Let psi in, psi scattered and psi total be the incident, scattered and total wave function of the system undergoing a nuclear reaction. Now this wave is assumed to be made up of large number of partial waves. Each one is characterized by a particular value of angular momentum L. This type of picture is only valid if the nuclear interaction potential is a central one. So with that in mind, one can write incident wave function with this expression, which is actually partial wave expansion of the incident wave. Only tells that each incident wave is made up of large number of partial waves. Each one is characterized by angular momentum L value. PL cos theta in this equation is a legendary polynomial. Sine of kr minus L pi by 2 by kr actually representation of the wave which is propagating along with the incident wave. So PL cos theta can be expressed in terms of spherical harmonics YLM, angular wave function. As the standard value of YL0 is written like this, root of 2L plus 1 divided by 4 pi PL cos theta. So that can be simplified to PL cos theta as YL0 root of 4 pi into 2L plus 1. So one can substitute that value in equation 1 and simplify it for incident wave function. Also, sine theta Euler equation, sine theta is equal to 1 by 2i times e power I theta minus e power minus I theta. So using that, one can actually expand and rewrite the incident wave function in this manner. And this equation can be further simplified to get incident wave function like this. So in this simplified wave function, what is actually happening here? So 2L plus 1 here in the denominator, root 2L plus 1 and 2L plus 1 here will actually become root of 2L plus 1, and 4 inside here square root will come out 2, and that 2 will and this 2 will get cancelled. So I in the denominator in this expression will go to this expression becomes I power L plus 1. So incident wave function then become summation onto root of 2L plus 1 times pi divided by kr times I power L plus 1 e power minus xl minus e power ixl into y of L0, where xl is a substitution for kr minus L pi by 2. So in that expression, above expression, e power minus kr and e power kr represent basically incoming and outgoing parts of the spherical wave. Okay. Therefore, because the scattered wave will go actually in both the direction. Superposition of these spherical waves actually generates a plane wave. That's why we represent incident wave as a superposition of e power minus kr of L pi by 2 and similarly e power plus kr minus L by 2. So total wave function exactly we can write in the similar manner, and however the total wave function must include one of the important interaction which is taking place between the incident and the target. So that information either lies in the form of change in the phase shift delta L, or as in the form of change in the amplitude modulus of eta L of the Lth partial wave. So you know that is important thing. So based upon that, the outgoing part will contain both this phase as well as amplitude information in the form of EL, eta L. So what is the difference between the incident wave function and the total wave function? So total wave function is after the interaction, whereas incident wave function is before the interaction. So the coefficient eta L is actually equal to modulus of eta L e power 2i delta L. So that eta L contains the amplitude information as well as the phase shift information of the interaction. This is normally called as inelastic parameter here. It's also called as S matrix in some other matrix formulation theory, which is a part of T matrix. So we are not going to study the T matrix, S matrix. We just keep our lecture only to this inelasticity parameter here. So the following cases of this inelasticity parameter are possible. So inelasticity parameter is given by the expression which is shown in the box here, eta L equals modulus of eta L e power 2i delta L. So based upon the value of eta L, we can actually get many things. When modulus of eta L is 1, then that expression eta L becomes just 2 power 2i delta L. So the eta L now then function of only the phase shift. Therefore, the total wave function now depends only on the phase shift, not on the amplitude. What does it mean? It means number of incoming particles equals number of outgoing particles. So there is no change in the number of particles. So this is a case of pure elastic scattering. So when eta L equals 1, that represents pure elastic scattering. The second case is when if eta L equals 0. What happens then? If eta L equals 0, then this entire eta L is also 0. That means psi total wave function contains only the incoming part of the wave. There is no outgoing part of the wave. It means complete absorption from the nucleus, target nucleus. So it absorbs whatever thing it is approached towards it. So hence it is called black nuclei, analogous to the black hole of astrophysics, in which star absorbs entire thing including the light. The third case is actually when eta L is less than 1. So when eta L is less than 1, then this quantity, when modulus of eta L is less than 1, then if times eta L will be less than 1. So that means the outgoing part magnitude will be less than the incoming value. That means partial absorption is taking place, which is a case of an inelastic process, a case of nuclear reaction. Complete absorption is also a case of nuclear reaction. The case 4 is when modulus of eta L is greater than 1. Extending this analogy, one can inform that if modulus of eta L is greater than 1 means the magnitude and intensity of the outgoing wave is more than the incident wave. That means generation of new particles. So this is a rare phenomena. It can happen, but not always. Okay, we are not going to discuss that case here. So let us go to the first case, pure elastic scattering. So in the case of elastic scattering, let us write scattering wave function. So scattering wave function can be computed from the total wave function and incident wave function as equal to difference between total wave function and the incident wave function. So using the equations for those two, one can write the scattering wave function in this manner. The first part in this expression is the total wave function. The second part represents the incident wave functions. So if you look at the equation, this part function is common in both the equation, total wave function as well as incident wave function, and YL0 is also common in both the wave functions. Therefore, scatter wave function, you can take that comma. If you take that comma, you get this expression. In this expression, what we have is e power minus ixl minus eta l e power ixl minus e power minus ixl minus e power ixl. So e power minus ixl in the first part here and the second part here, they will get cancelled. Then we have minus plus e power ikxl. So if you take common e power ikxl and if you simplify that, you can get the expression for scattering wave function, which turns out to be a simple expression like this. Summation of root of 2l plus 1 times pi divided by kr into I power l plus 1 times 1 minus eta l e power ikxl times yl0, spherical harmonic function. The scattering cross section, then we have to determine scattering cross section in order to compare with the experimental result. To do that, what we need is the number values. Number of Ni. N incident is the number of particles crossing a unit area per second and incidenting on the target. Similarly, what we need is N scattered, which is represent number of scattered particles per second and enters a sphere of radius around the interaction center. So scattering cross section then is defined as ratio of N scattered by N incident. This is actually the general definition for scattering cross section. How do you determine N scattered and N incident? Basically, N scattered and incident are actually fluxes of incident particle and flux of the scattered particle respectively. So that can be represented in classically in a different manner and quantum mechanically in a different manner. So quantum mechanically, those fluxes are determined from the probability current densities. So which is denoted as J, and they are defined like this. For N scattered, which is the integration over all angles of J scattered times R squared times d omega. D omega is the solid angle, and N incident is the incident probability current density itself. So whatever you estimate from the probability current density for incident wave, that itself is the incident wave. As for scattered wave, we have to integrate this over all angle because the scattering can take place in all possible direction. That's why. So probability current density quantum mechanical is defined by this expression, which is equal to h cross by 2im times psi star gradient of psi minus psi gradient of psi star, which is a definition for probability current density. Instead of using this complicated expression, one can use a simple expression like this: R of psi star times h cross by im times gradient of psi, where this R is a special symbol, denotes the real part of the argument of equation 5. Let us denote the first part, which is present in the wave functions, root of 2l plus 1 pi times I power l plus 1 by a symbol. I am calling that here as AL. So then the scatter wave function can be written in this manner. Psi scattered equals summation of AL divided by KR, where AL is defined here. Okay. So AL by KR times 1 minus eta L times e power IXL YL0. If that is the scatter wave function, then its complex conjugate can be written as this expression. So that all those terms which are complex, they get the asterisk sign here. That means they are actually conjugates of the corresponding parts. Exponential function e power contains imaginary part e power IXL. Therefore, the complex conjugate of psi is psi scattered will become e power minus ixl, and yl0, if it is complex, then it becomes yl0 star. That's the thing. Then let us calculate gradient of psi scatter. It's just a differentiation with respect to gradient with respect to r. So when you do that, you get this expression. From this expression, you can get r common. If you get r common outside, you get this pad. Psi scatter, gradient of psi scattered will be equal to summation of al by kr times 1 minus eta l e power ixl times ik minus 1 by r into yl0. So using these two values, one can estimate scattering current density, probability current density for scattered wave, which is defined by this expression, and substituting the value of psi star and gradient of psi scattered, you get this particular expression. In this expression, you notice that yl0 here, yl0 star, yl0 here, and e power minus ixl and e power plus ixl, they will get cancelled. And similarly, a power al star here and al here, you get modulus of al square. So simplifying that, you get the j scatter will be equal to that expression, and from that actually what we have to get is only the real part of this expression. So if you multiply this by that and you take out only the real part, you get the scattered wave function to be equal to modulus of al square divided by kr whole square times 1 minus eta l modulus of whole square modulus square of yl0 times h cross k by m. The product h cross k has a dimension of momentum. The scattered particles flux. After determining probability current density of scattered particles, we have to determine scattered particles flux through this expression, and substituting the JSC, you can get this expression, and note that this has an integral over all angles. So only this angular wave function, spherical harmonics, is the angular function, and other parts are actually free from angles, therefore you can take it outside. So the expression becomes simple like this. All other things are independent of angle, and this integration of il modulus il square times d omega is actually orthonormal condition of spherical harmonics that turns out to be 1. Therefore, scattered particles flux is a simple expression equals to modulus of al squared by k square times 1 minus eta l whole power square modulus square times h cross k by m. Note that r square here and r square here, they will get cancelled during simplification. Incident particle flux. Incident wave is a plane wave. It is represented by e power ikz, and therefore its complex conjugated e power minus ikz, and its gradient is k times ik times e power ikz. So using that, actually one can determine probability current density of incident wave using this expression, and you just substitute the values of psi star and gradient psi and take the real part of this, that gives the incident particles flux, which is equal to h cross k by m. So this incident particle flux itself is actually the probability current density itself is the incident particle flux. Therefore incident particle flux equals h cross k by m. So that's actually incident particle. We know incident particle flux, and also we know scattered particles flux. Taking the ratio of the two, one can estimate scattering cross section sigma sc. So if you take the ratio, this is common in the numerator as well as denominator, they will get cancelled. Then the scattering wave cross section become a modulus of al whole square divided by k square into 1 minus eta l whole square. Note that this al is actually notation which was given earlier by us. So you just substitute al here, then modulus al square will become 2l times 2L plus 1 times pi, and k is actually 1 by k is lambda bar reduced de Broglie wavelength, so 1 by k square can be written as lambda bar square. So substituting all these values in equation 10, one can write the scattering cross section in a simple manner like this. Sigma scattered will be equal to pi lambda bar square times a summation of 2L plus 1 times modulus square of 1 minus eta L. This is scattering cross section for total scattering cross section for all partial waves. So for one particular value of L, you get one partial scattering cross section. When the incident energy is very low, then only S wave is important. So for S wave L equals 0, then the cross section for S wave will become sigma scattered 0 not equals pi lambda bar square times modulus square of 1 minus eta naught. That's the expression for scattering cross section for all and also for one particular partial wave. Then reaction cross section. So reaction cross section can be determined exactly on similar lines. Only thing is one has to use the wave function, right wave function, to get the reaction cross section. So if you use that, then you can derive this expression for reaction cross section, which is pi lambda bar square times summation of 2L plus 1 times 1 minus modulus of eta L whole square. So this is the difference between scattering cross section and reaction cross section. For reaction cross section, modulus is now only for inelasticity parameter eta L. For S wave, okay, that can be determined by using total wave function, and I'm giving you this as an exercise to you. So in case of S wave, L is 0, then reaction cross section takes this simple form. So in summary, these are the actually two cross sections, scattering cross section as well as reaction cross section. Here you can notice the difference between the two. The difference only lies in the terms containing the eta L between the two types of cross section. Now let us discuss few special cases. So if you just look at these two expressions, scattering cross section can be maximum only when eta L is minus 1. Then the scattering cross section will be maximum. At the same time, reaction cross section will become 0. So when eta L is minus 1, scattering cross section will be maximum, that will be equal to 4 pi lambda bar square into summation of 2L plus 1. So at the same time, reaction cross section is 0. Okay. Now second case, when is reaction cross section is maximum. So reaction cross section can be maximum when eta L itself is 0. In that case, maximum value of reaction cross section is equal to pi lambda bar square times summation of 2L plus 1. So when this is that, then at the same time scattering cross section will be this value, pi lambda bar square times summation of 2L plus 1. And next, the third case, this implies, if you compare the maximum values of the two, it implies scattering cross section maximum value will be equal to 4 times the reaction cross section. So that's an important thing one has to understand. The third case is actually when eta L is plus 1. When eta L plus 1, what happens to scattering cross section, reaction cross section? Both will turn out to be 0. So if you look at the first case, in the absence of reaction cross section sigma r, there is a scattering cross section. So that means scattering can be present even in the absence of reaction. And look at the third case, when scattering is 0, then reaction cross section is also 0. So that's a very important information, and combining these, one can make a statement that reaction without some scattering is impossible, although scattering without reaction is possible. This is a very important information that can be understood from these special cases and also by understanding the two scattering cross section. So we have three values of eta L, and we have the cross-section values. These values can be plotted in a simple graph. So in this graph, the y-axis actually is scattering cross-section, and x-axis here actually reaction cross-section. Both are normalized by pi lambda bar square times sigma 2L plus 1. So this picture actually marks also 3 points for eta L equals 1, for eta L equals 0, for eta L equals minus 1. So within this actually there is a shaded region. That shaded region represents the region where actually reaction as well as scattering can take place. So there will be no reaction, no scattering when this eta value exceeds the shaded region. So that ends the lecture.